Hello and welcome back to the remainder of Chapter 10. So we just finished looking at equilibrium. Now we're going to tie that in with our acid and base chemistry that we were looking at the very start of Chapter 10. And so what we have here is a reaction called the autoionization of water, also known as the autoprotolysis, which is written right here. So think about what this autoionization means. Auto means it is happening on its own. Ionization obviously means it's turning into ions. So water can react with itself and transfer protons. And so we end up taking two water molecules where one of our water molecules is acting as the acid. And so it's able to take one of its hydrogens and donate it to the base. So one of the waters is acting as the base. So our base then is able to take on that extra proton to become the hydronium ion. So hydronium is now our conjugate acid, and the water that was the acid, since it started off as protonated and it lost its proton, it is going to make the hydroxide ion, which is our conjugate base. So this is called the autoionization of water. And we can write an equilibrium constant expression for this reaction. Now remember, in equilibrium constant expression, we do not include solids or liquids. So in this case, everything on the left side of our reaction is a liquid. So none of it will be included in our equilibrium expression. So when we're writing K, we would say it's the products, which is H3O plus, raised to its coefficient, which in this case is just 1, times the concentration of hydroxide raised to its coefficient, which is also 1. And then technically speaking, we would say divided by our reactants, but we don't have any reactants here to deal with. So if you want to write it over 1, you can. You don't need to write anything. But this is specifically called Kw. So we had Keq, we had Ka for acid dissociation, we had Kb for base dissociation. This is called Kw for water ionization. And the Kw that we're going to be using is 1.0 times 10 to the negative 14. And remember that all of these K values are specific to a given temperature. So our temperature here is going to be at 25 degrees Celsius. So unless it is explicitly written out in a question, we should always assume that we are operating at 25 degrees C, because that way we can use this value for our Kw. Remember, K does not have units, so there's no unit associated with the 1 times 10 to the negative 14. But let's talk about what this 1 times 10 to the negative 14 means. So recall from our equilibrium section that this number, since it has a negative exponent, that means that this number is less than 1. So which way does this reaction lie? Does this reaction lie to the left or lie to the right? In the case where we have a K value that is less than 1, that means that we lie to the left. In other words, we have more reactant than we do product. And this is great news for us because hydronium is very, very acidic. It is a very strong acid. Hydroxide is a very, very strong base. And think of all the things that we use water for. We drink it, we bathe in it, all of the many things that we see happening with water, and yet we don't get burned by strong acids or strong bases because this reaction mostly stays as reactants. But every now and then, it does convert into hydronium and hydroxide. but for the most part, we end up with just water, which is why we're able to use it for so many various things. So we can use Kw and use this equation in order to solve for our concentration of hydronium of an acid or of hydroxide of a base. So you need to have memorized this equation for Kw, that Kw equals hydronium times hydroxide, and you need to have the value of Kw memorized. So 1 times 10 to the negative 14. So everything that's in gray needs to be memorized for this exam. So let's take a look at how we can use Kw in finding concentrations. So in this particular case, we have a solution of barium hydroxide at 25 degrees Celsius. Now remember that little symbol is supposed to be an arrow. I'm not sure why it's not showing up. But barium hydroxide, when it's put into water, will dissociate into 1 barium ion and 2 hydroxide ions. So we're trying to find out what is the concentration of our hydroxide and what is the concentration of our hydronium. Well, since we have hydroxide directly in our chemical equation, it's probably best that we start there. So let's find our concentration of hydroxide. Well, we know the concentration of the barium hydroxide. It's 0.0030. So we can just write that here. And if we're trying to find the hydroxide concentration, remember that we can also think of 0.0030 as moles per liter, right? Moles per liter and molarity are the same thing. So if we're comparing barium hydroxide to the hydroxide, we can see that there is 1 mole of barium hydroxide for every 2 moles of hydroxide. And we're just getting that from our mole ratio directly from the balanced equation. So we have 0.0030 times 2. That's going to cancel out our moles of barium hydroxide, and we'll be left with 0.0060 moles of hydroxide over liters. And we know that moles over liters is molarity. So in other words, what we could say for the hydroxide as our final answer is that our concentration is 0.0060 molar. That's our concentration for the hydroxide. Again, all we did there was just simple stoichiometry. We're taking those coefficients from our balanced equation and using them to find our moles of hydroxide. Now that we have our moles of hydroxide, we can figure out our moles of hydronium. Because in any aqueous solution, recall that aqueous means that we are in water. So if we're in water and water auto-ionizes, that means that every solution has some amount of hydroxide and some amount of hydronium. So how do we find out how much hydronium there is? We use Kw. So I'll do this in a new color. We can say that Kw is equal to hydronium times hydroxide, and that will equal 1 times 10 to the negative 14. So we know our value for the hydroxide, which we can plug in. So H3O plus is our unknown. Hydroxide is 0.0060 molarity equals 1 times 10 to the negative 14. So now we just do algebra here. And in order to find our hydronium, we're going to divide both sides by the 0.006. And so once we do that, we end up with a hydronium concentration of 1.67 times 10 to the negative 12 molarity. So for our hydronium, that would be our final answer. And so that's how we can figure out our two concentrations here. Now notice that our concentration of the hydronium ion is very, very small. 10 to the negative 12 means we moved that decimal over 12 places. So it's important for us to note that the concentrations of hydronium and hydroxide are going to be inversely related. The higher amount of hydroxide you have, the smaller amount of hydronium you can have, and vice versa. So now we know how to find concentrations for various pieces given a concentration of a compound that's in solution. But let's look at how acidic or how basic a solution is. And we do this by looking at the pH scale. And you should be familiar with pH. You've probably heard about it in another class. But as we just saw, hydronium ion, which is also written as just the hydrogen ion. So hydrogen ion and hydronium ion mean exactly the same thing. So I don't want you to get confused if you're seeing one over the other. They are interchangeable. So H plus or H3O plus means the same thing because it's just water with that extra proton. So we just saw that our number was very tiny. It was times 10 to the negative 12. So instead of using that as our scale, we use a logarithm. And so a logarithm goes on a scale of 10, and it makes things just a lot easier for us to kind of pay attention to. If you're not super familiar with logs, that's okay. We'll talk about them. We'll make sure that you feel comfortable. But the reason that it's called pH is because anytime you see P, known as the P function, it automatically means negative log. So that means that the pH is the negative log of hydrogen concentration. And so again, here we have H3O plus written, but H3O plus and H plus are the same thing. So one way that we can kind of tell based on our concentrations before we get to actual pH is by just looking at our concentrations between our acid and our base. If we have more hydronium than hydroxide, then this is considered an acidic solution. If we have a combination of our hydronium and our hydroxide that are equal to each other, then this is a neutral solution. And if we have hydronium that is less than our hydroxide, that means we have a basic solution. So let's talk about what this pH scale looks like. And you have a list here of some common pHs of various substances that you're probably somewhat familiar with. So we can see that it starts off very acidic here, and then we work our way down into more basic solutions. So what do these numbers represent, and how did I know that 0.5 is very acidic and then 14 is very basic? So let me pull up a blank screen so that we can take a look at this. So on our pH scale, we have a number pretty much that goes from 0 to 14. And here, right in the middle, is going to be 7. So remember that Kw is equal to our hydronium times hydroxide, which means that if both of these values are the same amount, the same concentration, we can think of them both as X. So it would be X times X, or X squared, right? X squared equals 1 times 10 to the negative 14. This is the case when our hydronium and our hydroxide are the same. And so when they're the same, that gives us a neutral compound. So how do we determine what the pH will be if we're looking at something neutral? Well, let's solve for x. Go ahead and solve for the value of x by taking the square root of 1 times 10 to the negative fourth. Once you do that, you should get an x value of 1.0 times 10 to the negative 7 for both your hydronium and your hydroxide. Now remember, pH is looking specifically at the hydronium concentration. So we can then find the pH by P means negative log, and the hydrogen concentration we just solved for is 1 times 10 to the negative 7. So if you plug that into your calculator, you will find that the pH equals 7. So just to kind of clarify what we just did one more time, we said in the previous slide, hydronium and hydroxide have the same concentration. Our solution is considered neutral. So how do we find out what that concentration is? Well, if it's the same and we know that they're being multiplied together, we can just call it x squared. So we solved for the value of x, which we know is the value of hydronium, and then plugged it into our pH equation to get a pH of 7. So 7 here is our neutral part of our pH scale. If we have a concentration of hydronium that is higher than 1 times 10 to the negative 7, so if we have hydronium that is a higher concentration than 1 times 10 to the negative 7, we will end up with somewhere in this region, and this region is considered acidic. If we go the other way and we say that our amount of hydronium is less than 1 times 10 to the negative 7, then that will fall into this section, which is basic. So let's clarify a few things. The higher the concentration of hydronium, that is a more acidic solution. And the higher concentration you have of hydronium, the lower the pH is. So again, this is an inverse relationship between the H plus and pH. So as H plus concentration increases, pH decreases. One more time, as hydrogen ion increases, that means that pH decreases. So I just want to kind of put everything all together one more time before we actually start trying different questions. And so let's say if we have our line, so we said that on the left side, if our hydronium is greater than 1 times 10 to the negative 7, this means that we have a high concentration of H3O plus. And remember that the H3O plus and the OH minus are inverse as well. So this will be a low concentration of hydroxide. So anything from a pH of 0 to 7 is considered acidic. 7 we said was neutral. That's where our hydrogen ion and hydroxide ion concentrations are equivalent. And then we go to the other side, and we said here that if we have a hydronium ion concentration that is going to be less than 1 times 10 to the negative 7, we'll see here a low concentration of hydronium, which means we have a high concentration of hydroxide. High concentration of hydroxide, low concentration of hydronium, which means that we will have a pH that is between 7 and 14. So we'll have a high pH, and that means that it'll be basic. Okay, so this should kind of tie it all together, make sure that we understand our relationships. Okay, so now that we have looked at the pH scale, let's take a look at some practice problems. So we'll go back to the PowerPoint. All right, so this question is asking us to find the pH of human blood. And we're told that the hydronium ion concentration is 4 times 10 to the negative 8. So we know that pH is equal to the negative log of hydronium. All right, so how do we solve for pH? Well, let's look at what's given to us in the question. We have hydronium ion concentration. So for this problem, we can just go right ahead and plug in. So pH equals the negative log of 4 times 10 to the negative 8. And we'll find that the pH for this is about 7.40. Now notice that there are no units for pH either, so we're good to go there. Also, I want to point out that one way that you can double check if you've been doing your work correctly is to compare the first number of your pH to the number of your exponent. They should be very similar. If they're not very similar, then you know that you made a mistake somewhere. So 7 and 8, those are right next to each other. If we had something even as low as 6, that would be a bad sign. So usually we want our first number of our pH to be plus or minus 1 of our exponent. And that's how we'll know we're in a good spot or we did something correctly. So let's take a look at our next question, which is a little bit more difficult. This one is telling us that we have a basic solution. Recall that this has a hydroxide, so this solution is going to be basic. But we're looking for the pH. So we know that pH is our negative log of hydronium. Let's look at what was given to us here. We're told that we have a hydroxide concentration in this question. So for this particular question, we cannot just plug in our value. We have to do a little bit extra work. And so here's some extra work that we can do. There's 2 different ways to solve this problem. I'm going to show you the easier way first. I call it the easier way because I don't like to work with scientific notation if I don't have to, and most students have agreed that this particular method seems to be faster and easier. So I'm going to go that way, but you do whichever one you think is more straightforward. So what I'm going to show you here is that we can rewrite Kw. So we said that Kw is equal to hydronium times hydroxide. Well, we rewrite this equation by turning everything into a P function. So we can change this from pKw equals pH plus POH. It's the exact same equation, but now it's done with logs. So if you know anything about logs, that's why it turned from multiplication to addition. If you don't understand where that came from, don't worry about it. Just know this equation. Now pKW equals 14. So we can say that 14 equals pH plus POH. So what I can do here is solve for POH first and then subtract. So recall, P just means negative log. So POH means the negative log of hydroxide as opposed to hydronium, right? POH is the negative log of OH. So we're told our OH concentration, we can just go ahead and plug that in. So POH equals the negative log of 0.04 molar. That will give us a pH of 1.4. Now we can take this value and plug it into this equation. So we can say 14 equals pH plus 1.4. We do the algebra and we solve for the pH, and we get that our final answer for pH is 12 points. And that would be your final answer. And you're probably like, oh, that's a lot of work. But again, if I don't have to use scientific notation, I won't. I will choose this way time and time and time again. But this is just one method. Let's look at another method that you could do to solve this problem. So the other thing that you could do is take KW and start from there. So we said that KW is our hydronium times our hydroxide, and that is equal to 1 times 10 to the negative 14. Well, we have our hydroxide concentration right here that we can plug in. And so we can solve for H3O plus this way by saying that H3O plus will be equal to 1 times 10 to the negative 14th, that should say 14 up there, over our hydroxide, which is 0.04. And so when we do that, let's see what we get. So I'm getting 2.5 times 10 to the negative 13. Sorry, I had to count it. So 2.5 times 10 to the negative 13 here. This is our hydronium concentration. Now we can plug that into our pH equation. So negative log of hydronium, which is 2.5 times 10 to the negative 13. So if we do that, the negative log of 2.5, 10 to the negative 13. And so you should get, just like we saw before, something very close to 12.6 like we had last time. And again, we can double check it because we have negative 13 as our exponent and we have 12 as our number before the decimal. So that's a good sign that we're doing things correctly. Alrighty. So again, it's completely up to you how you would like to do it. You can either use KW equals H3O plus times OH minus equals 1 times 10 to the negative 14, or you can do 14 equals pH plus POH. Those are your two options here. So now let's look at how we can find our concentration if we're given a pH. So here we're told what the pH is. We have our pH here, but we're looking for the concentration of the hydronium ion. So this means we have to do the inverse of a log. So on your calculator, where you have your log button, you should see right next to that button, usually it's right above it, something that says times 10. That is your inverse button. That's what we want to do. So our inverse of log is 10 raised to the x. This is different from the button on your calculator that you use for scientific notation. This is a different button. Okay? So here, if our pH equals 4.83, the way that we solve for our concentration is we need to get rid of the log. So the way that we do that is we do 10 raised to the negative pH will give us our concentration of hydronium. Just like if you wanted to find hydroxide, you would do 10 to the negative POH equals the concentration of hydroxide. Okay, and we have to use negative pH or negative POH because we're doing a negative log. So we have to account for that. So in order for us to find our H3O plus here, we would do 10 raised to the negative 4.83. And when you plug that into your calculator, you should get 1.48 times 10 to the negative 5 molar. Again, we can double check. We have 5 versus 4. That's a good sign that we're on the right track. So try that out on your own calculator. Make sure that it's making sense for you and that you know which buttons you should be using. All right. So what happens here whenever we change our concentrations and we can change our pH? So remember that a weak acid will dissociate, but it doesn't dissociate completely. So we see here in this generic equation, HA is just a generic weak acid. It could be any weak acid, acetic acid, citric acid, hydrofluoric acid, doesn't matter. And it's going to react with water. We're going to see our hydrogen leave from the acid and go to the water. So now our water becomes hydronium, and our HA is just whatever the anion was. And so what we can see here is that our pH will affect how much of each conjugate we have. So recall, HA is our acid, which makes A minus our conjugate base. So in the case that we have a pH equal to a pKa, well, what is that? Remember, Ka is our acid dissociation constant. And pKa then means it is the negative log of Ka. So we can compare pH and the pKa of a solution to determine which species, the acid or the conjugate base, is dominant in our solution. So if pH and pKa are equal to each other, then that means that they have equal concentrations. If pH is less than our pKa, that means that we have a higher amount of acid. Remember, the lower pH means more acidic. So it makes sense that we would have more acid. If our pH is greater than our pKa, remember, high pH means more basic. So it makes sense that we would have more of our conjugate base here. So again, the whole purpose here is we can compare the pH of the solution to the pKa of the acid to determine which species, the acid or the conjugate base, is dominant in the given reaction. And this is important when we look at buffers. Now, a buffer is a weak acid with its conjugate base put together in a system. So that's why it's important for us to understand the acid-base conjugate pairs and why we had to look at that previous slide. So it's a weak acid with its conjugate base, and the whole purpose of a buffer is that it can resist big changes to pH. This is super important. We see buffers all the time in our bodies in particular. So in the case of an acid being added to a solution, the acid will react with the conjugate base of the mixture. So we said in the last slide that the conjugate base is thought of as A minus, and we're adding an acid to our solution. So we're going to represent the acid as H3O plus. These two are going to mix together to form the acid that was in the solution and water. So what happens here is we're adding a strong acid to a buffer system, and when we do that, we're just making water. And water has a neutral pH, so our pH isn't going to change very much when this happens. In the case of a base being added, it's going to react with the acid of the solution, HA. So remember our reaction was HA plus H2O makes A minus and H3O plus. So if we're adding acid, it's going to react here, right? Le Chatelier's principle, we're adding acid, it's going to shift this way. If base is added, it's going to react with the acid. And so base we represent as OH minus. So our H moves over, we're going to make A minus and H2O. So in either case, if we're adding acid or base to our solution, we're making water, which is why our pH is able to stay so constant. So what's an example of a buffer that we're likely to see, especially those of you that are going into healthcare? One of the most popular pH buffers that you should be familiar with is the pH of the blood. And blood is supposed to be held at a pH of 7.35 to 7.45 roughly. And we use lots of different things in our bodies to make sure that we stay at that pH range. If we get too acidic, bad things can happen. If we get too basic, bad things can happen. So there's a lot happening in our systems. And the way that this works is that cellular respiration happens in our body. And cellular respiration is the process of converting oxygen that we breathe in into carbon dioxide. So let me go write that out. Now, obviously, we need to get rid of that CO2. That's what we exhale. We inhale oxygen, we exhale carbon dioxide. So in order for us to get rid of that carbon dioxide, it has to be carried through the blood. And so it gets carried through the blood as one of these two species. This first one is called carbonic acid. And then the next one you should recognize is the bicarbonate ion. And so we have this reaction where carbon dioxide in the blood reacts with water in the blood. And from there, we end up making this carbonic acid solution. And so the way that it normally happens is we add, or we make our H2CO3, which can then react with more water in our solution or in our blood, and we end up making bicarbonate and hydronium. So hydronium, we know, we've seen it before, is a very strong acid. It can bring down your pH very, very quickly. So what can happen here is the Le Chatelier principle once again. So if our blood is too acidic, right? Acidic means we have a high concentration of hydronium. So if we're adding hydronium, we need to shift left. We need to get rid of the carbon dioxide so that our hydronium can be converted back into carbon dioxide and we can lower its concentration a little bit. So this is, for instance, why when we're exercising, we're breathing more heavily. We have a lot of cellular respiration going on. We're making a lot of carbon dioxide. So we need to increase our breathing rate so that we are getting rid of that carbon dioxide that we're making so that our blood doesn't become too acidic. So this is just one example of where we can see Le Chatelier's principle really happening in everyday life, something that we deal with all the time, as opposed to just a random chemical equation that you haven't seen before that doesn't make any sense. So one more time, when we're exercising, for example, we know that cellular respiration is happening more readily. So we're making lots more carbon dioxide. Carbon dioxide is going to react with the water in our blood to make hydronium. That's going to make our blood very acidic. So in order for us to bring our blood pH back up and make it roughly 7.35, we have to get rid of that carbon dioxide. And that's why you start breathing heavier so that you can expel that carbon dioxide and shift your reaction back to the left. All right. So that is the end of chapter 10. You know how to contact me if you have any questions about anything. Have fun.